So we just got done talking about inverse functions, and there's a pair of inverse functions that we're going to use a lot, and those are natural log of x and e to the x. So the graph that I drew for us yesterday, those are actually natural log and exponential graph e to the x. So this graph here is e to the x. This graph here is natural log of x. And because these are inverse functions, there's a lot of nice properties that we can use. Eventually, we're going to use one to help the other one. If I'm trying to clean up an equation, a lot of times we can use the opposite function to help us clear up certain parts that we want to, if we want to solve for x, so if it's x is stuck in the exponent, or if we want to solve for x that is stuck in natural log, we can use the other function to help clean up that expression. Okay, so okay, so if I want to solve this equation, 7 is equal to e to the x plus 1. So a little bit of review. Excuse me. So if I want to solve for x, notice how x is stuck in the exponent. If I want to get x by itself, I want to bring that x down. So we can involve natural log to help us bring that exponent down. So if I introduce logs into the equation, and if I introduce that natural log into the equation, natural log and e have a way of canceling each other out. And also, now that we are under an log property, exponents are free to move, right? So if I move that exponent down, and if you remember, one of the properties that we learned, natural log of e is equal to what? 1, yeah. So natural log and e, because they're inverses of each other, if I pair them up, they have a way of canceling each other out. So that goes away. And I'm just left with x plus 1 equals natural log of 7. Natural log of 7 is just some decimal value. If I want to solve for x, I just have to subtract the 1 over, and that's my answer. Okay, likewise, if I want to solve for x, but x is stuck inside natural log, remember, these are not independent expressions. I cannot distribute the natural log through because this is inside natural log. It's not like, if it was like natural log of x times 2x minus 3, then yes, then we can distribute this through because these are independent. But this is inside. If I want to solve for x, I have to find a way to undo that natural log. So the way I undo natural log is if I involve e, because I know that e and natural log have a way of canceling each other out. So the way that I get these together is I raise both sides with e as the base. Because I know that e and natural log have a way of undoing each other. So this will cancel out. The 2x minus 3 will drop down. And then we can have a much easier time solving for x. All right.
So like ln equals 1.
Natural log of e is equal to 1. E to the natural log of x is equal to x. So they have a way of canceling each other out. Either natural log of e cancel each other out, or e to the natural log cancel each other out.
Whatever every time you're gonna ask like the approximate value, is like e 7 something.
Right. Typically, no. But yeah, it's good to know that e, if you want to use a number to estimate e, then use 3 because it's close enough to 3. But yeah, it's 2.7. But if you're just doing a ballpark value, the number 3 is good enough, or at least give you some idea where that number is. Okay, couple of exponent properties here. If I have e to the a times e to the b, I can clean that up to be e to the a plus b. And if I have e to the a divided by a to the b, I can basically make it e to the a minus b. So if I want to multiply bases, I add exponents. If I want to divide bases, I subtract exponents. Remember that e is a number. So the derivative of e squared is not 2e to the first power. It's just going to be 0, right? Because e squared is like 8 point something. So a number, a constant's derivative is always just going to be 0. Okay, so we're going to introduce a new rule here, new derivative rule, and that is e to the x. But I'm going to call it e to the u so that we can kind of have that chain rule built into our derivative rule. So the 3 big rules, derivative-wise, that you're guaranteed to see on the AP exam is power rule, natural log, which we just did, and then e to the u. So those are the big 3. And then as far as trig goes, sine and cosine, you can most likely see those as well. So this is an important derivative rule to know. The nice thing about this derivative rule is that it's basically itself, right? If it was e to the x, the derivative is just e to the x times 1. So typically we consider this as the easiest derivative rule because it's just itself, right? It doesn't really change. We just have to be aware that if the variable in the exponent is more than an x, we got to worry about u prime. We got to do a little bit of chain rule for that. Okay, so we're going to involve some previous rules as well. So every time we introduce a new derivative rule, we're going to go back and we're going to kind of recap some of the rules that we learned in the past, whether it's product rule, chain rule, implicit, quotient rule. So we're going to revisit all those things that we learned in the second and third unit. Okay, so example 3 here. Find y prime for y is equal to natural log of 2x minus e to the negative 2x. So notice we can't distribute this through, right? This is stuck in this form. Okay, but we can identify this as a 1 big U value. Also, we don't have a log property to expand, right? This is not a multiplication, this is a subtraction. So we are stuck in this form, but we do have a U value that we can identify, and the larger rule that's going to make a bigger impact is this natural log of U rule. So we'll do U prime over U, and then once we're inside U prime, then we can worry about each of the individual rules. Okay, so understand this is the large U value that we're working with. Okay, so we're going to apply the rule here, U prime over U. All right, so what's the derivative of 2x minus e to the negative 2x? These are separated by subtraction signs, so these are independent of each other. So 2x is what? 2x's derivative is just 2, right? Yeah, 2. Minus, okay, and now we're into the new rule that we learned. E to the negative 2x becomes, all right, let's follow the rule. The derivative of e to the u is e to the u times u prime. So the derivative of e to the negative 2x is e to the negative 2x times negative 2. So the thing that to remember with e to the u rule is that the function, your original problem, will show up in the derivative. It will show up in the derivative. Okay. All over. So now we're back to the larger rule at play, right? U prime over u. What's my u value? This expression, right? So kind of these nested chain rules here. Let's see, what can we do to clean this up here? We can't cancel across addition and subtraction, but what we can do is we can clean up within the numerator and denominator separately. So numerator, we can bring this e down to the denominator. Now this can't cross this line here because this is attached to the minus sign, but it can be in the denominator within this region here. So we can make this 2 plus, well, the 2 negatives cancel out, 2 over e to the 2x all over 2x minus 1 over e to the 2x. Right, so we if these are being multiplied, then we can bring that e down to this denominator, but these are being connected by addition, subtraction, so the most that we can do is we can put in the denominator, but only the denominator within this space. We can't make it cross to the other side. Okay, so that's our derivative. Whatever this graph looks like, any x value I give it, I'll get a number, and that number will describe the steepness of this original curve.
Also, that's your binomial reading.
Yeah, this is the derivative. Yeah, this is y prime. Yep. Okay, number 4 here. This one is a little messier. Find y prime for y is equal to x times e to the x squared plus 2x plus 3 cubed. So we have a whole big e rule here, but there's something else going on. Can you recognize another larger rule that we have to involve? Product rule. Yeah, you guys see that? X is its own thing. This e to the x squared plus 2x plus 3 cubed is its own thing. These are being multiplied. We have to go through product rule.
The x is the only one separate from.
That's right. X is separate. X is separate from that e to the exponent. I'll put this on a separate page so I can make sure I don't run out of room. Okay, so let me write the new rule that we just learned here. Okay, so f prime, what's f prime? Just what? Okay. G, I'm just going to copy my g function down. Back to f. All right, so now we have an extended chain rule here. So the derivative of e to the u is e to the u times u prime. So what comes first? Right. How would you start off?
The chain rule comes first.
Okay, well, what does the rule say? The rule says the derivative of e to the u is what?
It's u times u.
Right, so what's e to the u? The exact expression, right? No changes, right? Because the thing with e to the u is that this is the derivative with a little bit of extra stuff going on. Okay, but first, you're just going to copy the exact same expression down because that's what the rule says, right? The e to the u is the derivative of e to the u. So now we can focus our attention on the exponent and what is required to find the derivative of this expression. We got to go through another set of what? Another chain rule, right? So this one is its own chain rule. So outsize derivative times insize derivative. So outsize derivative is 3 parentheses squared. Times the inside portion's derivative. So times what? 2x plus 2. So it's kind of like this nested chain rule, right? You got the outside, you got the inside, and you got the inner portion, and they're all going to get put together here.
You give that process again?
Yeah, sure. So we start off with the big rule here. The derivative of e to the u is e to the u times u prime, right? So e to the u, that's going to show up initially, right? And then u prime is asking, what is the derivative of this entire expression? So if I just gave you x squared plus 2x plus 3 cubed, you would go through a chain rule for this portion, right? So the outside portion would be parentheses cubed. The inside portion would be x squared plus 2x plus 3. And then we're having to go through that whole chain rule within this portion. So outside derivative is 3 parentheses squared times inside's derivative, which is 2x plus, oops, sorry, 2x plus 2, not 2x plus 3.
Also, 3 goes away.
That's right, the 3 goes away, and the 2x becomes a 2. Any questions there?
So you used like that parentheses expression.
That's right. The u is the original exponent. The u prime is do whatever it takes to find the derivative of this whole mess, which is its own shape rule. Okay. All right, let's continue looking at some more problems here. Example 5. Yeah, that's the answer. Yeah. Not going to ask you to clean up. This is messy, but that's our derivative. That's our derivative. Yeah.
Pretty like line to one, so it's like.
I mean, I could take out a GCF, but yeah, but you're right. I can merge that one into the expression. I could take out a GCF, but yeah, that's fine for now.
You combine the X and E for I'm just.
We can put them next to each other. We can put them closer to each other, but there's not a whole lot that I can do to clean that up beyond. I mean, beyond taking out the GCF of the E to the parentheses. Okay, number 5. Number 5 says write an equation of the tangent line. So tangent line means find order pair, which they give us, find the derivative, find the slope, and then point slope form. Okay, so if I already have order pair, next I need to find the slope. To find the slope, I need to find the derivative. To find the derivative, though, what's involved here? What do you see? Product rule again. Yep, e to negative x and natural log of x. These are separate expressions, right? I got to go through product rule. Okay, so the rule for e to the u is simply e to the u times u prime. So e to the u times u prime. Okay. G function, no changes. Back to f. And then what's the derivative for natural log of x? Yeah, u prime over u, right? So just 1 over x.
It's like the same thing that in the last one, but with f.
Yes, right. Yeah, same thing. It's just that instead of the g being the e, I have the f being the e to the u, but still the same rule. It's a lot easier for this derivative since the u value is a lot easier to work with. Just e to the u times u prime. Okay, so I don't really care about cleaning up my derivative because all I care about is getting the slope. So I just have to plug a 1 in and get some number out of this so I can pull the slope at this point. Okay, so this is some number here, but the nice thing is, what's the natural log of 1? 0. That's nice, right? That's going to wipe this whole thing out. So I'm just left with e to the negative 1, which I can reduce to be just what? Or how can I rewrite this with a positive exponent? 1 over e. And 1 over e is just its own number. It's some decimal, but we'll leave it in exact form. So that's my slope. Right? And we'll just put in the point slope form. All right, question with 5. How to get 1 over e? So, so we went through product rule, and then I plugged in 1 in for all the x's. And then I just try to clean this up here. Natural log of 1 is 0, so that's going to wipe this whole thing out, right? And then e to the negative 1 is the same thing as 1 over e if I put that e in the denominator. And then anything times 1 is just 1, so I'm just left with 1 over e. Okay, number 6. Find the derivative, find dy dx. Okay, there's 2 things that I want you to point out here. What do we have to be concerned with when we're working this derivative?
The y.
Okay, yeah, something with the y. So what do you notice about the y? Because the y's feel out of place, we have to implicit. Yeah, good. So we know we have to keep track of our dy dx's, right? Okay, one more thing. Product rule. Yeah, you see how x and e to the y, they are distinctly different expressions. They're being connected by multiplication. We got to go through product rule here. Okay, so we'll go through the product rule, and then apply the derivative rule as needed. And then how many dy dx's do we expect to show up in our derivative line? 2, right? You see 2 y variables, so you expect 2 dy dx's. Okay, all right, so. Okay, so one piece at a time. X becomes 1 times g back to f g prime. Okay, what's the derivative of e to the y? Remember, the rule for e to the u is e to the u times u prime. So e, good, e to the y times 1 dy dx. All right, 10x becomes 10. 3y becomes good. All right, we don't want to, even though the y disappears, we still need that dy dx to show up. All right, so now it gets a lot easier. Now you're just rearranging and trying to solve for dy dx. So the terms that include dy dx, I'm going to group them on the left side so that I can eventually factor that dy dx out. So again, with implicit, you're still getting a derivative. You're still getting some slope formula. It's just that usually with implicit, you just need a little bit more information. Sometimes they need both the x and the y value to produce the slope of a point on the curve. Okay, example 7. Everybody good here? So example 7 says, find the equation of the tangent line to the graph of the function at the given point. So really, it's the same thing as example 6, or similar to example 6, except we have one additional step to find the slope and then point slope form, right? So very much similar process as example 6. We just have to go one step further and find the slope. Okay, so here's example 7. Okay, so again, what do you notice is involved in the derivative process?
A y.
Yeah, implicit and how many times though?
12.
Twice. Yeah, we gotta do with the product rule twice. Yeah. Okay, let's do the first pair here. X f prime is just 1. Back to f. G prime, e to the y becomes. Good. All right, f prime. dy dx. Good. Good. E to the x times 1. Yep. So this one has no dy dx because it's not asking for y's derivative. Okay, now equals to what? 0. Okay, we saw 2 y variables. We should be expecting 2 dy dx's, and we have that. Okay. That's a good way to kind of double check that we're not producing less or more than we need. Okay, so now we can do what? Solve for dy dx. Now I do want to talk about a little bit of a shortcut here. This problem is not asking for the derivative equation. It's only asking you for the tangent line equation. So all we need is the slope. So to make this a little faster, we're still going to solve for dy dx, but if I can go ahead and just replace all the x's and y's with 0 and 1, things will just merge a little faster because there's less variables to keep track of. Some things will begin to cancel out, and we can just move faster towards getting that slope that we want. I mean, we could solve for dy dx. It just takes longer because we have to keep track of all these variables. But if all the variables can disappear at this point, then we can kind of accelerate the path towards getting to what we really want, which is the slope. It's not asking for the derivative equation, so we don't really need to keep track of all of our x's and y's at the end. So I'm going to take that shortcut. Replace all the x's and y's with 0 and 1. And then if I just clean this up and then get dy dx by itself, I'm going to get to the slope a little faster. Okay, so e to the what? E to the, what's the y? E to the 1. Okay, so that's just e, right? Plus x, what's x? 0. That's nice, right? It's going to wipe this whole thing out. Plus dy dx e to the e to the 0. Now, careful here. Sometimes we expect 0 to wipe everything out, but if 0 is in the exponent, that's not going to quite wipe this whole thing out. E to the 0 is what? It's 1, right? So this is not 0. If the exponent is in the 0 value, that is still going to leave us with a number. Okay, so this is still going to stay. Plus y times e to the x. Y is 1. 1 times e to the 0 equals 0. Okay, so the e to the 0 is just going to be 0. So I have e plus dy dx plus 1 equals 0. So it's a lot faster, right? Now I can just get dy dx, and then all the x's disappear and y's disappear. I'm just left with some number, and this number will represent my slope. So this is my slope. Yeah, we just have to kind of keep reminding ourselves that E is not a variable, right? E is just some numeric value. So now that we have our slope in our order pair, we can do point slope form. Y minus y1 equals m times x minus x sub 1. Okay, so our homework is going to be on page 16, 33 through 46 all. We have some time, so why don't we get started, and I can also show some answers as we go along. So page 16, 33 through 46 all. Okay, so I put some helpful derivative rules up here. E to the u is e to the u times u prime. I'll put up another one here. Natural log of u is u prime over u. Let me just kind of go through and highlight some important first steps, right? If we can figure out the first step, then everything kind of falls into place. 33 through 36, this is pretty straightforward, right? Just e to the u times u prime. But starting with 39 to 42, what do you see? All these require what? Yeah, they all require product rule, right? All right, so we see that we have distinct expressions that are outside of each other. Okay. What about 43? Chain rule, yep, good. This is again just e to the u times u prime. 45 and 46, this involves natural log. 46 though. We can actually avoid quotient rule by involving what? Is there a log property that we can do before the derivative process? Quotient property, right? Natural log of a over b can be expanded to the natural log of a minus natural log of b. So that will allow this to split up into two easier problems, and we can find the derivative that way. This one, keep in mind, we got to go through u prime over u here. We cannot distribute that natural log through, right? Okay, all right, good. Go ahead and start this. There's my derivative rule for e to the u. Here's my derivative for natural log of u. So what's 33 here? I want to follow the rule. E to the 2x becomes what? E to the 2x times 2. Thank you. So with e to the u, the derivative will have the original function show up. The original function is always part of the derivative. So you can just really just copy the original function down, but you don't have to worry about that u prime.
So you know to e in the u.
What do you mean?
The e to the u, and it's just times u prime.
Yeah, that's right. Just e to the u times u prime. So,
So just ignore the e for the u prime.
right, that's right. Yeah, you ignore the you ignore the e for the u prime because u prime is just the exponent. The u prime is just talking about the exponent. Okay. 35 is similar, right? E to the u times u prime, but we should rewrite that root x as what?
1/2.
Yeah, x to the 1/2, and then we'll go through a power rule with that x to the 1/2, right? I think 36 feels pretty straightforward. You're just doing e to the u times u prime, taking care of the exponent's derivative. Product rule is needed for the next few problems. Recognizing that we have distinct expressions that are outside of each other and they're being multiplied with each other.
Is there a reason that interest rate a lot more like complex than it could be?
I guess because we're involving, it's not like power rule where it's just X. Now we're involving more additional symbols, so it just maybe that feels more complicated. And also things can't merge as cleanly as before. We kind of have to leave things.
So you can't really simplify it.
Yeah, because we have different families of functions now. It's not like all x's. Now we have e to the x, you have natural log of x, you have polynomials, so they all kind of need their own distinct space. We can't put them cleanly together as before. So number 40 should feel like 39. Product rule. Oh, number 40. That 4x is making it difficult. Now, if it was e to the 4x plus 4e to the 4x, then I can make it 5e to the 4x. But that x is kind of getting in the way. But what we could do is, if you wanted to, you could factor e to the 4x out and make it 1 plus 4x. That's fine. You can do that. Okay, you guys will finish off the rest of this page for homework. And I will check this tomorrow. I'll send out a link to the key so that you guys can check your in. All right, go get your phones. Great.